So this is going to be a break from machine learning because it's cosmology and astrophysics introduction of talks which will be given by two young people in our team. So I will introduce the motivation and context of our research. So as astrophysicists and cosmologists, we are interested to trace back the history of our universe, and much of what we have learned over decades, I would say centuries of work is kind of summarized in this picture. You have the history of our universe from today, where the telescopes are, all the way to the Big Bang, the furthest out point we have in our models, and eventually there is something I will show here. You have at some point the universe becomes optically thick, and so you cannot see beyond some surface here, which is about a few 100,000 million years after the Big Bang. But through the observation of this image here, of this signal, we can infer and try to study what happened before. So there is a lot of questions, and we have, in a way, a model which describes the universe and is able to use to interpret observations. But there are a number of questions which are addressed here. And more, the problems become more and more complicated, as you will see, because the data becomes a very high precision, and you run into difficulties which were not faced before. And the one which we are working on is this one, that eventually in the observations, you integrate the photons, the light from across the universe, all the way to our galaxy. And the galaxy has this interstellar matter. It is the matter out of which new stars are formed. And today, many of the questions we have about our universe raise this question of how you separate the emission from our galaxy from the cosmological signal you are looking for. And this is our entry point in this field, because myself, I am an expert in the physics of the interstellar medium. So to show you some of the data, this is observations which were obtained by this space mission, Planck, European Space Mission, with an American collaboration. And this is the image of our universe. It's the celestial sphere projected on this surface, which shows you the granularity, all the structures which led to the universe as we see it today, as the galaxies, the stars, planets, and ourselves. Everything started from this, and those fluctuations which are the seeds of the universe today, at that time were very, very small. Those structures here, which trace the structure of the universe after 3,000 years after the Big Bang, are 1 part of 10 to the 5. So very small fluctuations which we are able to measure with incredible accuracy. And there is one more dimension to these observations, is that we can also measure the polarization of the light, and which gives further physical information about the universe. And here the polarization is encoded into texture. You see it has a very specific texture which encodes the polarization. So what do we do as astrophysicists and cosmologists to study this signal? And so these signals are Gaussian, so the natural way to analyze them and do physics with them is to do power spectra. And this is what is illustrated here to show the incredible dynamic range of these observations. So you have several power spectra which are shown here. You see the huge breadth of these signals compared to these anisotropies in what we call temperature, in total brightness. And here you have terms which encode polarization, which is divided in what we call this E and B mode based on different topological symmetries on the sky. And at the end, this is not the end of the story, because we are looking for a signal which is somewhere at the bottom of this plot here, and which observations are starting to be sensitive to. And this signal is particularly important because it will be a signature of the primordial gravitational waves. So it will be an experimental test of the present model we have about the cosmic inflation, exponential growth of the universe at the time of the Big Bang explosion. a few years ago, and there was an experiment in Antarctica, which called the bicep cake, which claims that they had possibly detected this signal, and they observed this part of the sky. And what you see here on this part of the sky, this is an image again from Planck, but this time it shows you the emission from our galaxy with this texture, which shows the direction of polarization, which relates to the magnetic field which pervades our galaxy. And you see that in this region, there is not only cosmological signal, there is emission from our galaxy. And what we know today is that this emission from our galaxy is dominant. So you cannot really conclude on the cosmological signal which we are looking for without understanding clearly what are the statistical characteristics of this foreground. And so it has been the key. And so the difficulty here, so the way, if you want to move forward, we would like to extend the statistical approach which people use to analyze the signal, the CMB signal, to the foregrounds. But the difficulty, obviously, is that this is a much harder task because those foregrounds are highly non-Gaussian. So the way we proceed as astrophysicists, we have a lot of expertise knowledge on what is happening as the physics of this interstellar medium, and we try to go from this to a statistical modeling of the non-Gaussian data which characterize this medium. Obviously, this is an iterative process, and this is where what we do. And to show you some insight into this problem, I've gathered here several images at different scales of this interstellar matter. This is a whole sky view. Again, you have this whole sky projection of the Planck data on this balloon, this oval balloon, and this is the celestial sphere, and you see the imprint of the galactic disk, and even outside of this galactic disk, you see this structured emission from the interstellar matter. And other satellites give us some sharper view of what is happening to show the multi-scale structure of this medium. If I zoom on this area with these other observations, you see I see this, and here the colors encode spectral variations, so changes in the properties of interstellar matter across frequencies, which shows the complexity, another direction of complexity of this signal. And if I further zoom with another observation from another satellite, I get this. And so you see, we have an impressive set of data which shows this multi-scale structure of interstellar medium, but so far we have no model. And this is really an outstanding difficulty for this cosmology interface, but also in general to understand how this medium eventually leads to the formation of stars, and so contributes to the general evolution of the visible matter in the universe and the formation of galaxies, stars, and planets. So there is this is an outstanding problem in astrophysics also, to have how do we model this to be able to understand how this matter contributes to the evolution of the universe. And so based with this problem, I went to see Stefan, and we said, can you help us? And the idea which we will pursue, and you will see some of the early results we have obtained working with Stefan, is that we are trying to use the machine learning approach to reach a statistical description of this medium, which we could use for component separation for the cosmology, but also for our interstellar medium physics as well. There are many applications which are possible, and they are all, I think, quite far-reaching. So one of the difficulties we have compared to possibly other problems in machine learning is that we have only one sky. It's not like we can have a database of many skies. There is only one. So we have to learn from the data, but there is only one sky. So you will hear more about this tomorrow with a talk of Erwan and Bruno, who will show you our early results. Thank you.
us, like starlight polarization data. There's been work by Susan Clark and by Alex Azarian and their group showing the correlations between H1 and the dust polarization directions. Have you thought about generalizing? I mean, we have this additional data
Yes.
that gives us very strong priors on the structure. Have you thought about using that in combination of the data?
Well, I think this is part of the approach we would like to have, because we are all inspired by how cosmologists are able to bring different data sets together through the lambda CDM model. We would like to have a statistical model which basically can help us bring all of these absorption constraints into the game. I think right now it's difficult because we don't have such a model. So we go through empirical correlations, but it's very difficult to come out with firm conclusions out of this.
Azarian will claim they have a model.
Yeah. But will you trust that we will detect the primordial B modes just based on that? I think it's each time the observations are incomplete. They provide constraints, but they are incomplete constraints.
They give us more information than we would have otherwise.
Yeah.
I mean, as you know, my experience with the bicep results, I'm not someone who believes them immediately.
Yes.
All right. So we've seen some very nice talks about the impressive ability of deep nets to extract information about complex data sets. But we've also had some questions yesterday about understandability and interpretability. So the main point of this talk is to take the discussion to the other direction and try to see how we can use networks to gain insight in complex data sets. So this is work that I've done with Dalia Baron, graduate student. And to set the stage, let's look at one very practical example. So here's a data set. It's an astronomical data set. What we have here is about 1,000 spectra on top of each other. So every row of this image is an object, a vector. If you don't know what they are, don't worry, because if I show this to astronomers, they also don't know what these spectra are. And the reason is that this is very messy. Okay, there is no order here. And typically when we have a data set, often in science, we like to ask questions like, simply what do I have in my data set? Are there different populations of objects? Are there trends? Are there outliers, etc., etc.? And that takes a lot of work trying to understand the features we have in the data, etc. But wouldn't it be great to be able to just take an arbitrary data set and automatically turn it into a reordered version that would reveal its intrinsic structure? So this is what this algorithm is about. It's called a sequencer, and it can go from the left to the right without any free parameter. And it's trying to do that in a way that is as generic as possible. And so what happens is that here, when I show this image to astronomers, they suddenly realize those are emission lines. We are seeing objects at different redshifts. This is a redshift sequence, etc., etc. And then they can recognize that those are quasars. So how can we do that? In 10 minutes, I will not have a lot of time to go into the details. But here's the key idea. If I look at the difference between what I have on the left and the right, and I think of these systems as statistical systems, basically on the left, I have something that's random or hot, and on the right, it's cold, or it would be the solid equivalent, if you like. Now, if I describe these data sets, if I describe the similarity between the objects as graphs, if I look at the shape of these graphs, what I find is that on the left, it would be a spherical graph. It would have no shape. But on the right, I have something that is very elongated. And so this is a very strong sign. It's a geometric property that is telling me that there is something flowing through the data when it's ordered this way. There is a very simple trend that can be extracted. So I'm going to make use of this property, so a geometrical property of networks that describe the data set, to basically find that answer automatically. All right, so the very quick view of how this works, I can start with my randomly ordered data set. And I'm going to look at it on all scales. So this is, it has similarities to what some of the deep nets do. So I want to look at all scales, and I want to compare the similarity between objects using as many metrics as I want, okay, to be as generic as possible. And basically what we do in practice, we use L2, we use KS, and we use Wasserstein. And we can add more if we like. Then what I'm going to do is that for each of these scales and metrics, I'm going to look at these graphs, and I'm going to look at their shapes. And each time I see something that is elongated, I know I'm not getting this by chance. Okay, it is there for a reason. There must be a simple trend in the data underlying this graph. So I know on which scale, for which kind of metric, there is relevant information. Then what I can do, I can combine all these scales and all these metrics informed by the shape of these networks. I combine all of this into one final network, and I can walk through this network, find the shortest path, and that's going to give me the final sequence. Okay, so that's the idea. It's a different use of networks to gain insight in the data. So here the idea is to end up with simplicity. So some examples, those are more astronomical data sets. The first one is the one you've seen before, quasar spectra. I can reorder this just by pressing a button. I have another set. Again, astronomers do not always recognize these objects. But here what I have are stellar spectra, spectra of stars. When I reorder them, I find something very different. So here the information is on large scales. In the first example, it was on small scales. And what I find is a sequence of stars ordered by temperature. So the main trend you see in the middle, going from upper left to lower right, is the peak of the black body spectrum of these stars. And so we see the temperature going from hot to cold. Another data set, again, this is real data. This is data from the Sloan Digital Sky Survey, so it has noise in it and all sorts of weird objects. I can reorder it. What I see here, again, I find a redshift sequence. But in addition, I can see that at the top, I have a different population of objects, and so this algorithm is also capable of doing classification, and it has understood on its own that there are different types of objects in this data set. And finally, to show you that this is as generic as possible, I can reorder this data set with exactly the same technique, and I get this. All right, so this is completely agnostic about the data, and it has, using this geometric information, it has its own way to find the meaningful trend, the meaningful way to reorder the objects in the set. So this is a way to do dimensionality reduction. So what we end up with at the end is a one-dimensional manifold along which the data is distributed in the most elongated way. And you might ask, okay, what about other techniques out there to do dimensionality reduction? Could I get the same results? So we've done some testing and comparisons. So in the CS world, the technique that's been used the most to do dimensionality reduction is t-SNE. I guess many of you know about it. And so this is an example where we start with an idealized data set, which is just a diagonal line. We add noise to it, we randomize it, we run the sequencer on it, and this is what we get. It's not perfect, but it's close to. And this is the setup in which 99% of t-SNE users run the algorithm, the t-SNE algorithm. And because it is based on an L2 metric, it's not capable of finding the trend in this case. So our sequencer has more sophisticated metrics in it. So you might say, okay, why don't you inject that metric into t-SNE to have a more fair comparison? And we've done this. This is what you get. And an important point I forgot to mention here is that when you run t-SNE, this is not parameter free. Okay, t-SNE depends on two things: the learning rate and the perplexity parameter. And in order to get any result with t-SNE, one has to tweak these two parameters until one finds a satisfactory answer. So in contrast, the approach that I presented here with the sequencer has no free parameter. So in one shot, you get to the result directly. So that's interesting. So you might say, okay, if t-SNE with a Wasserstein metric, in some cases it might give you the right answer. Does it generalize? The answer is no. If we go back to the Einstein example, okay, in this case, the sequencer works very well. It uses Wasserstein to do this reordering, but in comparison, t-SNE fails. So the key point here is that there is a nice regime in which I think this new algorithm has something to bring to the table. It is capable of finding interesting trends in complex data sets in a completely unsupervised way and without any free parameter. So there is no need to tweak this learning rate or perplexity to find something meaningful. So we've applied this to a number of data sets and have made some discoveries. I'm going to flash 2 of them briefly. There are lots of astronomers in the room. So I'm going to give one astronomy example. We've looked at spectra of quasars. And this is only based on about 2,000 objects. And this is data that's been public for almost 20 years. And we've run the algorithm on it. We find a sequence in the data. It turns out that nobody had seen this before. We looked at it more closely, and we found a very interesting relation between basically the properties of black holes that live at the center of galaxies and some large-scale properties of galaxies on scales that are about 4 orders of magnitudes greater. And nobody thought of looking at this correlation before. And this is the first thing that the sequencer showed us. I'm not going to go into the details. This would be a talk in its own, but we ended up with a new way to estimate black hole masses using this technique, which is quite interesting. And just for the astronomers in the room, we can now extend the so-called M-sigma relation. It's a relation which connects the mass of a black hole to the mass of a galaxy, so quantities that are on vastly different orders of magnitude. People had measured this based on a couple of 100 points before. We can now extend that to 10,000 points and more. And this opens up a completely new avenue to study galaxies and black holes. Again, this is based on public data. And what has happened is that the sequencer has shown us a relationship that was in the data, but nobody had seen it before. Outside of astronomy, this is another interesting example. Here, I'm going to process a series of seismograms. Okay, so we have this time series. We have seismograms that are recorded at many locations all across the US. And what I can do is to simply reorder all of them and build a simple color scale to show the index of these seismograms, put that on the map, and as you can see, we find these beautiful regions with different properties, showing properties of the crust all across the US. And to show you that what we get is not completely off, and the black contours here show the geological map of the US, so the different types of rocks as a function of position. I could go on with more examples, but time is short. We've also discovered what is called post-cursor waves in public data. So nobody had seen this before. Those are waves that come a little bit after. They are much weaker. They are seismic waves that propagate through the Earth. They are reflected at the core mantle boundary deep into the Earth. People thought that this boundary is very smooth, but these post-cursor waves tell us that there are actually features at the boundary, and there are scattering effects that retard the waves. So all of those are simple trends that emerge naturally out of the data thanks to the sequencer. It also works in 2D, and I'm almost done. We can just, without any training, reorder digits in the MNIST data set. Okay, so this is to show that we can do images, not just one-dimensional objects. And I'm going to almost stop. So machine learning is great, but if machine and me can learn, that's even better. And in order to do so, what we need is to come up at the end with simplicity. Okay, so we need to look at complex data set and extract from them simple trends that can be described using the language of physics or statistics, but in a concise manner, not necessarily using millions of parameters. And so this approach, which makes use of geometrical properties of networks, allows us to get there. And without any free parameter, we can extract meaningful trends out of complex data sets. We can look at all the scales in the data, and we can do that without any training. And I'm going to stop there just to say that we can extract these meaningful trends, and we can restore the visual insight that is so precious if we want to do scientific exploration. Thank you.
Break immediately afterwards. We'll be able to discuss so that we can take up a little bit of break.
Sure.
Okay, thank you. I just want to thank the organizers for organizing this. It's a very nice workshop. So I'm going to talk about a problem which we were trying to apply some methods from stochastic analysis, and what we know how to do in stochastic analysis is to look at path of functions or features on paths and try to apply it to an area where it's not perhaps immediately clear where paths arise. And this area is going to be topological data analysis. Joint work with Harold Oberhauser and Vijay Nanda, who are both at Oxford now. Okay, so what's the core of topological data analysis? Well, the main tool there is persistent homology. And the idea is that we've got some problem or some data sets, and we want to understand the underlying topology or the shape of this data. So situations where this might apply is sort of coverage of sensor networks, or something that arises in biological structures like proteins, or distributions of galaxies or clusters. So just on that picture down the bottom, we can see how sort of persistent homology works in a pictorial way. So you start off with a point cloud, and then around each point you grow little balls of certain radii, and then you increase this radii. And as they grow, you change the underlying topology of your structure. So here I'm looking at the homology of these guys. So you can see that the blue shape changes, and then it creates sort of, you start off completely disconnected, then you connect some of the points the moment that their balls overlap, and you keep on going. And then at the end, you end up with just a big blob. And so you're interested in the transition of this homology, in particular, when do features become alive and when they're born, and when they die. So the final output that we look at in persistent homology is called this barcode. So we encode all of this information through the sequence of birth-death pairs. So you can see that the blue lines down the bottom represent when a certain feature is born and dies. So this is the 0th level homology. So it just counts the number of connected components. And then sort of you can look at higher level, higher dimension homologies. And that's going to be the red line down there that counts the number of cycles inside your data. Okay, so we have this barcode, and we know that it's supposed to represent some sort of topological information about your data, but then how do you actually get that data? Okay, so this is a non-trivial problem, and it's received quite a lot of attention in the literature. And it's not easy because this barcode, it lives in a non-linear metric space. So how do you, sort of most scalable machine learning algorithms that we use they rely on some sort of a linear structure. Okay, so there's been some proposals. So one of them is just an embedding into a linear space, and there's some proposals like persistence images of atoms and our persistent landscapes of Bubinic. And then there's also some kernels, which, so once you have a kernel on an arbitrary set, you can always just apply your favorite kernel learning algorithm for this. So, and the other point that I might come back to later as well is that for large point clouds, it's also very computationally expensive to produce these barcodes. So it'll be nice to have a way of getting around that. Okay, so as I mentioned, one of the things that we like to do in stochastic analysis is to look at paths. Okay, so there's no sort of immediate paths here, but then perhaps we can somehow extract disordered data and learn from it. So in particular, the motivation for this is that we know a good features on paths, and this is the signature, which was also mentioned in talk yesterday. I'll come back to that on the next slide. So the proposed pipeline for this would be you map barcodes to paths, and then paths to signatures. Okay, so what is the signature, and why do we want to look at it? Well, we know that if we've got a random variable that takes values in an arbitrary linear space, then a useful and very common feature that we look at are polynomials. So polynomials in the abstract setting are products of linear functionals on this variable. And so we know under good assumptions, the expectation of these polynomials, they characterize your random variable. And you can also approximate sufficiently regular functions with these polynomials. Okay, so the signature is a generalization of polynomials to unparameterized paths. So if you believe that your data somehow is parameterization invariant and it's time ordered, and it's really the time ordering that you're after, then this could be a good feature to look at. So the explicit representation of the signature is given by this one of the ways of looking at it is given by a sequence of iterated integrals. Motivation for that is that this sequence of iterated integrals exactly what arises when you run Pickett iterations into ODEs. So, for example, if you know that the function that you're trying to learn is somehow the solution of a differential equation driven by this path, then this is exactly the correct object to look at. So, so coming back to persistent homology, what's a natural way to get paths from your data? Well, we call these embeddings. So we embed a barcode into the space of paths. So two of the embeddings that are present here are the so-called Bettian embedding. So it's a great simplification for your big complicated barcode down into a simple finite dimensional path. And what it measures is that at every single point in time, it just counts the number of homological features that you have in dimension n. So this gives you a sequence through the integers, a time-ordered path through the integers. And a simplification of that is that you look at this Euler embedding, which is the alternating sum of your Betti numbers. So this is a special linear combination of your Betti embedding. And so the nice thing is that the Euler can actually be computed without knowledge of the barcode, because Euler characteristic is actually something which is a feature that you can just count through counting the number of simplices rather than computing the barcode, which is potentially a powerful feature. Okay, then another one which, so there's another embedding which kind of captures the geometric properties of the path, and that's that you look at all of your, you order all of your barcodes, and then you look at the envelope that envelops these objects. So here the time is no longer the the radii of the ball, which was the natural way that you get to the time ordering. Here it somehow doesn't correspond to this filtration parameter, but it still captures the overall geometry of your barcodes. Okay, so we ran some experiments to sort of see how well this performed against other TDA methods. So we tried this out on three experiments. So we looked at this a popular texture image classification task. Another one was that we looked at a dynamical system, and so you've got this formula for a dynamical system, and your task is to learn this parameter r that appears in there. And you can see that as you change your parameter r from, say, 2.5 to 4.3, your sort of samples, they change. But you don't know how you visited these points. They're just given to you as a point cloud, and you're trying to figure out the r from there. Okay, and then the last one is you start off with some sort of a shape, and then you sample points from the shape subject to noise. So say there are 6 shapes here, so completely random. Then you sample from a circle, a sphere. This is a bit of a toy example. It's very synthetic data, as was the previous one. But this was just a test run to see how we did against other methods. So the results were a bit of interesting. That so here just notationally, K represents that this is a kernelized version of the feature map that we were looking at, and phi represents that we're actually looking at the feature map. So the classifiers that we used were support vector classifiers for the kernels and random forests for the actual feature maps. And so we performed with some of the embeddings fairly well on 2 of the data sets. And annoyingly enough, we actually really improved the performance because we ran ourselves the 2 top lines are the other popular methods in TDA. Annoyingly enough, we actually really improved their performance when we implemented ourselves. So that's at least for the persistence images one, life. So okay, so what's the final remarks on here? So well, this kind of gives potentially a new way to explore how you can actually extract features from these barcodes, and sort of potentially for the directions, like 2 immediate further directions where you could look at this, is that this Euler characteristic that I mentioned is very interesting, that you can compute it without the barcode. So it'll be tempting to apply it to large data sets where it's out of the question to compute the barcodes directly. And another place where you could apply the same philosophy, but potentially completely independently of everything that I was just saying before, was that it's a very interesting question to look at evolution of barcodes, which kind of represents an evolving network. Trying to see if the signature can actually tell you something about this path through barcodes is an interesting question. Okay, so thank you for your attention. And here are some references.